Everything around you is moving right now. Even though it feels perfectly still, the earth beneath your feet is rotating once every 24 hours. That simple motion is the reason day turns into night and night turns back into day. But that rotation is only the beginning. At the same time, Earth is also racing around the sun, completing one full orbit every year. And the sun itself is not fixed in space either. It is traveling around the center of our galaxy, a journey that takes roughly 200 million years to complete just once. Zoom out even farther, and the picture becomes even stranger. The entire galaxy is rotating billions of stars, including our sun, all circling a common center in a vast cosmic disk. When astronomers point telescopes toward distant galaxies, they see the same thing again and again, giant spirals slowly turning through space. Rotation is everywhere, and it doesn't stop at galaxies. Look closer, much closer. Weather systems rotate. Hurricanes spiral across oceans. Tornadoes twist violently through the air. Even the small whirlpool that forms when water drains from a bathtub spins. Across every scale of reality, from the largest structures in the universe to the smallest motions on Earth, rotation appears again and again. So the question naturally arises, why? Why does everything spin? Why is rotation so common throughout the universe? Why don't objects simply move in straight lines forever? And if planets orbit stars and moons orbit planets, and everything seems to be circling something else, why doesn't it all eventually collapse and crash together? To understand the answer, we need to start with something familiar. Right now, the moon is orbiting Earth. It has been doing this for billions of years. It doesn't drift away into deep space, and it doesn't fall straight down and collide with Earth. Instead, it moves in a graceful, continuous circle. The moon is traveling at about 2,000 miles per hour, an incredible speed. So why does it follow a curved path instead of a straight one? Two things are happening at the same time. First, the moon wants to move in a straight line. That is the natural behavior of any object in motion. But second, Earth's gravity is constantly pulling the moon inward toward Earth's center. The moon is always falling toward Earth. At the same time, it is moving sideways fast enough that it keeps missing. That combination, falling inward while moving sideways, creates a curve. And when the sideways speed is just right, that curved path closes into a circle. The moon doesn't fall into Earth, it falls around Earth. This is what an orbit truly is, continuous falling that never reaches the ground. The same principle applies to Earth itself. Right now, Earth is falling toward the sun. Gravity pulls us inward constantly, but Earth is also moving sideways at about 67,000 miles per hour. That sideways motion causes the sun's gravity to bend Earth's path into a stable orbit instead of a collision. Every planet in the solar system behaves the same way. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune are all falling toward the sun while moving sideways fast enough to keep missing it. This balance between inward pull and sideways motion creates orbits that can remain stable for billions of years. But this leads to an even deeper question. Where did that sideways motion come from in the first place? Why was everything already moving sideways before gravity started pulling objects together? To answer that, we need to go back to the beginning. The universe began in an extremely hot, dense state. As it expanded, energy turned into matter. Tiny particles formed, and eventually atoms, mostly hydrogen, filled space. Over time, these atoms gathered into enormous clouds of gas, stretching across light years of darkness. These clouds were not perfectly still. Nothing in the universe ever is. Small disturbances were everywhere. Shock waves from distant stellar explosions, gravitational tugs from nearby regions of mass, temperature differences, and random fluctuations all introduced motion. Different parts of the same cloud drifted in different directions. Some regions moved faster, some slower. Some rose while others sank. The motion was chaotic and unorganized. Then gravity took over. Slightly denser regions of the cloud pulled more strongly on their surroundings. As they attracted more gas, EY became denser still, strengthening their gravitational pull even further. This created a runaway process. Slowly at first, and then faster and faster, the cloud began collapsing inward under its own gravity. As the cloud collapsed, something crucial happened. All of those tiny motions within the cloud were carried inward. Some of them canceled each other out. Motion to the left canceled motion to the right. up canceled down. But the cancellation was never perfect. There was always a small leftover imbalance, a tiny net rotation. That small amount of rotation, barely noticeable at first, was enough to understand why. Imagine an ice skater spinning with their arms stretched outward. They rotate slowly. Now watch what happens when they pull their arms in close to their body. Without pushing off anything, without adding energy, the rotation speeds up dramatically. This effect occurs because of a fundamental law of physics called conservation of angular momentum. When rotating mass moves closer to its center, the rotation accelerates. The collapsing gas cloud followed the same rule. As gravity pulled the cloud inward and made it smaller, any tiny amount of rotation, it already had begun to speed up. What started as slow drifting motion turned into a noticeable spin. As the collapse continued, the rotation became faster and faster. And as the spin increased, the cloud began to flatten. Material that was once spread in all directions became squeezed into a rotating disk. The rotation pushed material outward, but only in the plane of rotation, while gravity pulled everything inward. The result was a thin, spinning disk of gas and dust. This process is unavoidable. Any collapsing cloud with even the smallest initial rotation will flatten into a spinning disk. It is built directly into the laws of physics. At the center of this disk, gas piled up. Pressure and temperature rose as more material fell inward. Eventually, the core became so hot and dense that nuclear fusion ignited. Hydrogen atoms fused into helium, releasing enormous amounts of energy. A star was born, and that star was spinning. The birth of a star is not the end of the story. In many ways, it is only the beginning. When a star ignites at the center of a collapsing gas cloud, the surrounding material does not simply vanish. Vast amounts of gas and dust remain, still orbiting the newborn star in the same flat, rotating disk that formed during collapse. This structure is known as a protoplanetary disk, and it is the birthplace of planets. Inside this disk, every particle is already moving. Each grain of dust is circling the star, carried along by the same rotation inherited from the original cloud. Over time, these particles begin to interact. When tiny dust grains collide gently, they stick together. These slightly larger clumps then collide with other clumps, growing gradually in size. This process is slow, taking millions of years, but it is relentless. Dust grains become pebbles. Pebbles become rocks. Rocks become boulders. Boulders grow into massive bodies called planetesimals, early building blocks of planets. As gravity takes hold, these planetesimals collide and merge, forming full-size planets. Here is the critical insight. Planets do not start moving after they form. They are already moving before they exist. Every particle that becomes part of a planet was already orbiting the star inside the rotating disk. When those particles combine, they retain their sideways motion. The planet inherits its orbit. It has no choice. This is why planets do not fall straight into their star. Their motion was built in from the very beginning. This explains one of the most striking features of our solar system. All 8 planets orbit the Sun in the same direction. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all move along nearly the same plane, like grooves on a record. This is not coincidence. It is a direct consequence of their shared origin in a single rotating disk. If planets had formed independently from separate clouds, their orbits would be chaotic. Some would move clockwise, others counterclockwise. Some would orbit at steep angles, others nearly vertical. But that is not what we observe. Instead, we see order, alignment, structure. The reason is simple. They all came from the same spinning disk. The flatness of planetary orbits follows naturally from this process. The original disk was thin compared to its enormous width, millions of miles thick, but billions of miles across. Planets formed within that disk, so their orbits remained close to the same plane. This flatness is one of the strongest pieces of evidence for disk-based formation. Planets themselves also rotate. Earth spins once every day. Mars rotates at nearly the same rate. Jupiter completes a rotation in just 10 hours. Saturn in about 11. Each planet spins for the same reason everything else spins. As material fell onto the growing planet, it arrived from slightly different directions, carrying angular momentum. The imbalance was never perfect. A net rotation remained. As the planet accumulated more mass, that rotation increased. Once a planet starts spinning, there is nothing to stop it. In space, there is no friction to slow it down, no air resistance, no contact with other surfaces. Rotation continues indefinitely. Billions of years later, planets still spin just as they did when they formed. Moons follow the same fundamental pattern. When planets grow large enough, their gravity can trap surrounding material, forming smaller rotating disks around them. These miniature disks behave just like the original disk around the star. Particles collide, stick together, and gradually form moons. This is why gas giants like Jupiter and Saturn have dozens of moons, all orbiting in organized systems. Our moon likely formed in a different way, but the result is the same. A massive impact early in Earth's history blasted huge amounts of material into orbit. That debris formed a rotating disk around Earth. Over time, the material coalesced into the moon. Different origin, same physics. A rotating disk creates orbiting bodies. Now zoom out even farther. Our galaxy, the Milky Way, is itself a rotating disk. Hundreds of billions of stars orbit the galactic center. Our sun is one of them, located roughly halfway out. It takes about 200 million years for the sun to complete a single orbit around the galaxy. During your lifetime, the sun will barely move along that path. But over cosmic timescales, it has completed many full revolutions. Why does the galaxy spin? For the same reason everything else does. The Milky Way formed from an enormous collapsing gas cloud vastly larger than the one that formed our sun. That cloud had some initial motion, tiny and random. As gravity pulled it inward, that motion was amplified. The cloud flattened into a rotating disk. Stars formed inside it. Those stars inherited the motion of the disk and have been orbiting ever since. Look beyond our galaxy and the pattern repeats. Most galaxies are spirals, massive rotating disks of stars. Some are elliptical, less structured, more chaotic in appearance. But even elliptical galaxies contain rotation. Their stars move in complex but still organized paths around a central mass. Rotation is not an exception. It is the rule. This is why the universe has structure at all. Without rotation, gravity would pull matter straight inward. Gas clouds would collapse into dense spheres. There would be no disks, no planets orbiting stars, no stable systems. Everything would pile up into featureless clumps. Rotation prevents complete collapse. It introduces balance. Matter falls inward, but sideways motion keeps it from crashing all the way in. Orbits form. Disks spread out. Structure emerges. Galaxies, stars, planets all arise from gravity working together with rotation. Life itself depends on this balance. Stable orbits create consistent environments. Planets can maintain steady temperatures. Stars can burn for billions of years. Without rotation, the universe would be far more violent and far less hospitable. And this brings us back to the original question. Why don't planets crash into stars? Why doesn't the moon crash into Earth? Because everything is always falling and always missing.